In this video, we are going to explore the basis of drawing so-called Lewis structures of organic molecules. When we refer to a Lewis structure, the first thing we need to get in mind is what type of features a Lewis structure shows us. A Lewis structure is going to show in every molecule that we draw, it's going to show all of the atoms, meaning for organic molecules, all of the carbons, hydrogens, and then whatever heteroatoms there are, such as oxygen, nitrogen, halogens, etc. It's also going to show all covalent bonds as lines connecting individual atoms like we see here. And it will also show, as a requirement, all unbonded electrons. So in other words, all lone pair electrons. And I'm going to abbreviate lone pair as LP here, or LPS in the plural sense. In later videos, we are going to look at abbreviated ways of drawing organic compounds. We start here with Lewis structures because ultimately Lewis structures are what provide us the broadest depth of information. So in drawing Lewis structures, let's go ahead and get started with an example problem to illustrate how we go about drawing Lewis structures, laying out some of the foundational work. So we're going to be asked here to provide the Lewis structure of acetic acid based on the skeleton that we provide below. And in this structure, we're going to assume here, because the problem tells us to assume, that there's no formal charges on any atoms. What we're doing here is we're starting with, in this example problem, a partial Lewis structure where I've filled in some of the components for us, and it's our job to fill in the others. So I'm drawing our structure of acetic acid here. This is a cool and relevant molecule because it is the component of vinegar that makes vinegar acidic. So vinegar has some percentage of the solution is water and some percentage is acetic acid. Acetic acid is the active component here. So this is our structural formula that is not showing the lone pair electrons. And for a Lewis structure, fitting that definition, a Lewis structure shows all the atoms. It shows all of the bonds, and it shows all of the lone pairs. And in this case, since a Lewis structure shows all the atoms, bonds, and lone pairs, it's the lone pairs that are missing in our structure here. And so we're tasked with filling those in. Well, how do we go about filling those in? A key clue here is we have to be given the information that there's no formal charges on any of the atoms. And as we saw in the last video, we were calculating formal charges. Stable molecules have a strong preference for having an octet on all of the atoms, except for hydrogen. Hydrogen is an oddball that its valence has 2 electrons in total, so hydrogen is going to typically have 1 covalent bond. But stable molecules, generally what we're going to see is that they have a complete octet on all of the non-hydrogen atoms and no formal charge on any atoms. And we learned how to calculate formal charge in the last video so that we are ready to think about how to arrange this molecule so that it has no formal charge on any atoms. So that's going to be our grounding basis here, is that we want to ultimately, when drawing Lewis structures, we want to make sure that the structure is going to have a complete octet on all of the atoms, and unless otherwise specified, no formal charge on any of the atoms. So how do we go about doing that when we're tasked here with providing the lone pair electrons onto this structure? We can't just go in and start filling in randomly lone pair electrons here, there, and everywhere, because ultimately each atom brings into the structure a certain number of valence electrons based on what column of the periodic table the atom is in. And that number of valence electrons brought in by each atom, if we sum it up, gives the total number of electrons that we have to work with. And those electrons can either form covalent bonds, which is what we see shown explicitly here, or they can be part of lone pair electrons. And so what we need to do here is look at the periodic table in order to fill in our lone pairs into this Lewis structure. The approach that we're going to take is we're going to find the total number of valence electrons that we have to work with. We're going to subtract the number of electrons that are in covalent bonds, because those are going to deduct from the number available. And then we're going to fill in the remaining unused electrons as lone pairs to accomplish two things. One, fill the octet of all of the atoms within the molecule, and two, make sure that we're arranging them so there is no formal charge on any of the atoms. So let's go ahead and start into this approach. We're going to need our periodic table in order to do that, so I'm going to go ahead and pull that up into our image here. You can get this image off of the Canvas website for the course. So I have brought in here a very small version of our periodic table. Small version is all we need. Let's go ahead and following our outline here for our approach, and this is a good general approach that you can use for anytime you're solving a problem with drawing Lewis structures and you're trying to sort out what some possible arrangements are here. So find the total number of valence electrons. Let's go ahead and calculate that. Total valence electrons. Calculating that based on the column of the periodic table is what's going to indicate to us how many valence electrons are brought in. So hydrogen brings 1, column 2 brings 2, skipping over to here, avoiding the transition metals, 3, 4, for example, carbon brings 4 valence electrons, 5 for nitrogen, 6 for oxygen, 7 for fluorine, 8 for these full octet atoms such as helium. So our total number of valence electrons here, taking into consideration what we have, and I'm going to highlight these as we go through to make sure that we've counted everything. So we have 2 carbon atoms, and the carbon is in the 4th column of the periodic table, so 2 carbon atoms. So I'm putting 2C for 2 carbons times 4 electrons per carbon would give us 8 electrons in total there contributed to the valence from the carbon. Our oxygen atom, or atoms I should say, I'll highlight in green there, there's 2 oxygens. So I'm going to put 2O, and that's O for oxygen, not a 0. And each oxygen atom is going to contribute, if we look over at our periodic table here, oxygen 6th column of the periodic table, so each oxygen is going to contribute 6 electrons. So I do 6 times 2 would give us 12 electrons total brought into the molecule via the oxygen atoms. And then our hydrogen atoms, looking at those, we have a grand total of 1, 2, 3, 4 hydrogen atoms. And so counting up those hydrogens, there's 4 hydrogens, and each hydrogen, since it's in the 1st column of the periodic table, brings 1 electron. That's going to give us a total of 4 electrons contributed by the hydrogen atoms. So we tally that up. 8 plus 12 plus 4, no calculator really needed for this, gives us 24 electrons that we need to plug in to the structure. Now, continuing on here, we found our total number of valence electrons was 24. We're going to subtract the number of electrons that are in covalent bonds. So number of electrons in covalent bonds, we count up the number of covalent bonds in total here. I'll go ahead and do that and highlight those as we go. So there's 1, 2, 3, 4, 5, 6, and then the double covalent bond counts twice, so 7, 8. So there's a total of 8 covalent bonds in this molecule, and each covalent bond contributes 2 electrons. And so it would be 8 covalent bonds times 2 electrons per bond. 8 times 2 makes 16. So it'd be 24 minus 16 electrons that are in those covalent bonds. So I'm going to put covalent bond electrons down here to keep count is 16 electrons total. So we do 24 minus 16 gives us our remaining electrons that we need to fill in. So 24 minus 16, I believe, is 8 electrons. So 8 electrons is the grand total that we need to fill in. And the goal of filling those in is going to be to fill the octet on all of the atoms and have no formal charges on any of the atoms as we fill those in. So plugging in electrons up here into our structure to fill the complete octet, we think about, first and foremost, I recommend plugging these in whatever way we need to do to fill a complete octet on each atom. So our oxygen here has 2 covalent bonds, so that takes care of 4 of the electrons that it needs in total. And then if we do 2 sets of lone pair electrons, that would bring us up to the octet. So I'm doing a lone pair here to spread those as far apart from one another as possible rather than showing them both on the top side of the molecule. Generally we show one on top and one on bottom to spread those out. And that would allow this oxygen atom to have a complete octet because there's 2 covalent bonds. Each covalent bond contributes 2 electrons, so that'd be 4 electrons, and then 5, 6, 7, 8 for our lone pair electrons in total. So that fills the complete octet for that oxygen. And if we were to use that formal charge calculation that we looked at in the last video, our formal charge we would find on that oxygen is 0. That's always going to be the case when oxygen has 2 covalent bonds and 2 sets of lone pair electrons. That's why that's a really common motif that oxygen will adhere to. Similarly, here with the oxygen that's part of a double bond leading to carbon, the oxygen has 2 covalent bonds. As we saw over here, it's just the 2 covalent bonds are going to the same atom, which is fine. Doesn't affect the count at all. And then 2 sets of lone pair electrons would allow us to have a formal charge of 0 on that oxygen here. Now, this is used, as we show these lone pair electrons, all 8 of our remaining electrons. So when we're down here at the bottom, we'd calculate the total valence electrons that we had available that each atom is bringing in based on its column of the periodic table. Then we looked at how many covalent bonds there were and multiplied the number of covalent bonds by 2 to come up with how many electrons are in those covalent bonds. Subtracting the total number of electrons in the molecule, or in other words, the valence electrons, minus the number of electrons in covalent bonds gave us 8 electrons left over to work with. We filled those in everywhere that there was not already an octet in order to bring those atoms up to the octet to show us where the lone pair electrons would reside within this molecule. And that put lone pair electrons on each of these 2 oxygen atoms, and it is indeed a total of 8 electrons because we have 4 sets in total of lone pairs, with each set of lone pair bringing 2 electrons, so that's 8 total, giving us our complete Lewis structure here, where the goal of this particular problem was to fill in the lone pair electrons into this partial Lewis structure skeleton that we were provided. In the upcoming videos, we'll continue to apply these strategies for drawing molecules, and we will also start to look additionally at some abbreviated ways of drawing molecules where you might not always need or desire to show all of the lone pair electrons and all of the bonds explicitly, but instead it might be more streamlined and convenient to be able to abbreviate some of that information or imply some of that information rather than drawing out all of the details of it. So we'll get into that in upcoming videos. Stay tuned.